The tremendous blast is a thought that has framed how we could decipher the universe, outlining the supporting of current cosmology according to Einstein's speculation, additionally known as coarse reading cosmology. The immense blast was the second. The universe started its development, indicating the creation of all matter, energy, and presence. This event occurred roughly 13.8 billion years ago and sparked the enormous universe we notice today. However, late developments in cosmology suggest that the colossal blast most likely wasn't the absolute beginning. Rather, there might have been a phase before the gigantic explosion that was comparably critical in shaping the universe as far as we might be concerned. This prepper period is known as incalculable inflation. Development is quite possibly one of the most interesting pieces of present-day cosmology. It suggests that before the hot, thick time of the enormous blast, the universe went through an unbelievably quick emotional development. During this period, the universe was duplicating in size at a shocking rate. To precisely account for how extreme this extension was, assuming the universe started smaller than an atom, it would have extended to be incomprehensibly larger than the entire discernible universe within a minuscule fraction of a second, around 1/4,000,000th of a second. This extension stage didn't last long, but it assumed a critical role in shaping the universe. When the inflationary stage completed, the energy driving this extension was released into space, warming it up and creating the particles of matter that make up all that we find in the universe. In numerous ways, this development precedes what we consider the immense blast. While the hypothesis of extension is generally accepted in cosmology today, numerous unanswered questions remain. For instance, we don't yet understand what started development, what made it stop, or how long it lasted. These are open inquiries in cosmology, and answering them is significant for a deeper comprehension of the starting point of the universe. Before development, the universe was in a staggeringly dense, small place of matter, often referred to as a peculiarity. From this peculiarity, development began and eventually led to the arrangement of atoms, particles, stars, and worlds. The possibility of the colossal blast as the start of everything is engaging, but present-day cosmology suggests a more complicated image. Some hypotheses suggest that the universe went through a phase before the gigantic blast. During this stage, extension made the universe develop at an incredible rate, expanding in size by basically a factor of 1,000,000,000,000 in a fraction of a second. This quick extension was fueled by a bizarre structure of energy that penetrated void space. At the point when extension completed, the driving force's energy was transformed into particles, warming the universe and prompting the hot, thick state we call the gigantic blast. This inflationary stage was cold and void, but it set the stage for material production and the universe we see today. One of the more theoretical thoughts in present-day cosmology is the concept of eternal inflation. This hypothesis proposes that inflation didn't shut down at the same time. Rather, it halted in patches, creating a variety of pockets, each of which could be a universe in its own right. Our universe is only one of these patches. According to eternal inflation, there could be a limitless number of these universes, each with its own arrangement of actual regulations and constants. This is where the possibility of the multiverse becomes an integral factor. The idea that our universe might be one of numerous, or even an endless number of universes, suggests that if this thought is correct, we would understand why the universe is so finely tuned for life. In this multiverse situation, each conceivable combination of actual regulations could exist in various universes, and we end up living in one where conditions are perfect for stars to form and for carbon, oxygen, and different elements essential for life to exist. While hypotheses like eternal inflation and the multiverse remain speculative, the possibility of inflation itself is grounded in observational proof. The most grounded support for inflation comes from the inestimable microwave background radiation, CMB, the oldest light in the universe. The CMB was emitted about 380,000 years after the tremendous blast, when the universe cooled enough for atoms to form. By then, the universe became transparent, and this light has been traveling through space from that point forward. By concentrating on the CMB, cosmologists can essentially take a baby picture of the universe. The light provides clues about the universe's earliest days, helping researchers understand what happened soon after the immense blast and offering support for the inflationary model. One of the most significant discoveries came from the European Space Agency's Planck satellite, which took detailed pictures of the CMB. These pictures reveal subtle variations in the temperature of the universe's earliest days, and these variations match the predictions made by inflationary theory. This trial evidence fortifies that inflation isn't simply a theoretical idea, but a significant piece of how we grasp the universe's starting points. Comprehending the enormous explosion and what went before, it requires bringing together two of the main theories in Einstein's current physical science: the theory of general relativity and quantum theory. General relativity describes the enormous scale structure of the universe, including the conduct of galaxies, stars, and planets, while quantum theory describes the conduct of particles on the smallest scales. To answer the fundamental inquiries in cosmology, such as what the universe is made of and where it came from, researchers must develop a hypothesis that joins these two systems. This would allow us to comprehend not only the colossal blast, but also all the conditions that prompted it. One of the most shocking parts of the universe is its size. The most far-off objects we can observe are around 47 billion light-years away, meaning the noticeable universe is around 94 billion light-years across. This might seem abnormal given that the universe is only 13.8 billion years old. How can the noticeable universe be larger than the time it would take light to traverse it in the age of the universe? The response lies in the reality that the universe has been expanding over time. As the universe grows, the distance between objects increases, making far-off objects farther away than the time it would take light to reach us. Most researchers accept that the universe stretches out far beyond the discernible universe. In truth, it's possible that the entire universe is boundless in size. The detectable universe is basically the part we can see, limited by how much time light has had to travel since the tremendous blast. There may be vast regions of the universe that we will always be unable to see. While it's possible the universe is infinite, the inquiry remains. Is there anything beyond the universe? Most researchers feel a little uncertain about this thought. If the universe is endless, there is no outside to it. The universe would simply continue forever, regardless of whether. Since the universe is constrained, it probably won't make sense to talk about anything past it. Past would infer something beyond space, which is one of the properties of the universe, so the possibility of past the universe most likely won't have any physical meaning. Similarly, as the start of the universe is a subject of incredible concentration, so too is its inevitable end. The best current gauge is that the universe will continue to grow perpetually. This is due to a strange peculiarity known as dark energy, which is causing the universe's expansion to advance quickly. Before the revelation of dark energy, researchers trusted that the universe's expansion would ultimately dial back due to the gravitational draw of matter. There was even a likelihood that the universe could stop expanding and begin contracting, prompting a big crunch. However, dark energy seems to be pushing the universe apart increasingly fast. If this acceleration continues, the universe will continue to grow endlessly, ultimately arriving at a state where galaxies float so far apart that they become segregated from one another. In this situation, the universe would become cold, dull, and exhausted. Stars would wear out, worlds would float apart, and matter would ultimately rot. This is referred to as the Big Freeze, or heat death of the universe. The narrative of the universe, from the enormous blast to its conceivable end, is one of the most critical and complex stories in science. While we've learned an extraordinary amount about the starting points of the universe through the hypothesis of expansion and the investigation of the vast microwave background, many inquiries remain unanswered. What caused expansion to start and end? What lies past the visible universe? Do we have a multiverse? And how many additional universes exist? As researchers proceed to concentrate on the universe utilizing advanced innovation and hypotheses that bind together quantum mechanics with general relativity, we will, without doubt, gain deeper insights into these mysteries. The journey to comprehend the universe is continuous, and every disclosure brings us one bit nearer to noting the extreme inquiries concerning our existence. The investigation of the universe's beginnings and structure isn't simply a logical attempt. It additionally raises philosophical inquiries about presence, reality, and our position in the universe. One significant area of interest in cosmology is the nature of dark matter, which is accepted to make up roughly 27% of the mass and energy of the universe. Not at all like normal matter, dark matter doesn't radiate, ingest, or reflect light, making it imperceptible and perceptible only through its gravitational consequences for noticeable matter. It is fundamental to figure out dark matter for making sense of the development and conduct of universes. Progressing studies and perceptions have given bits of knowledge into the properties of dark matter, but its definite nature remains tricky. Only a few candidates have been suggested, including weakly interacting massive particles, WIMPs, axions, and other exotic particles. However, up until this point, no immediate proof of dark matter particles has been found. The search goes on, through a mixed legend of terrestrial trials, astrophysical perceptions, and recreations that model how dark matter influences the massive construction of the universe. One more key area of exploration is dark energy, the secret force driving the sped-up extension of the universe. Dark energy contains around 68% of the universe's absolute mass energy content. Its revelation was surprising and has prompted numerous hypotheses, including the cosmological constant and dynamic fields. Understanding dark energy is essential, as it will decide the extreme destiny of the universe. Researchers are concentrating on its impacts on cosmic structures and attempting to decide whether it remains consistent over the long run or advances. Notwithstanding dark energy and dark matter, the investigation of huge-scale structure development offers huge experiences into the universe's set of experiences. Observations of the inestimable web, a tremendous organization of systems, bunches, and fibers, have revealed how matter bunches together, affected by gravity, prompting the perplexing designs we see today. Reproductions run on supercomputers assist specialists with understanding how these structures shaped over billions of years and continue to advance. Astrobiology, moreover, converges with cosmology as researchers try to figure out the circumstances essential for life beyond Earth. The look for exoplanets, planets circling stars outside our group of planets, has grown, with thousands found in ongoing years. A portion of these exoplanets exists in their stars' habitable zones, where conditions might be right for fluid water to exist. By considering these far-off worlds, researchers hope to learn more about the potential for life in a different location in the universe and the factors that make a planet cordial to life. At long last, the job of central material science in cosmology can't be exaggerated. The mission for a unified hypothesis that joins general relativity and quantum mechanics proceeds to challenge physicists. Speculations like string hypothesis and loop quantum gravity intend to connect these two areas, offering clarification for peculiarities like black holes and the early universe. As innovation propels, so does our capacity to notice and decipher vast peculiarities. Space telescopes, like the James Webb Space Telescope, are altering how we might interpret the cosmos by offering unprecedented detail of far-off systems and cosmic occasions. With each groundbreaking perception, we move closer to unraveling the mysteries of the universe's arrangement, advancement, and extreme destiny. The examination of the universe is a rich embroidery of logical requests and philosophical reflection. From the key powers that shape huge designs to the look for extraterrestrial life, our investigation is a demonstration of humankind's persevering interest in the universe. As we endeavor to answer these significant questions, in doing so, we acquire a more profound appreciation for the immeasurability and intricacy of the universe.